Hello, Calculus. These are the video notes for antiderivatives. So this is the beginning of the last module in calculus, focused on antiderivatives and integrals. A function f is the antiderivative of a function f if f prime of x is equal to f of x for all x in the domain of f. And basically what this means is we know how to take derivatives. How do you undo them? So if I give you the derivative, can you create the original function that it came from? The only warning here, and this is a big deal in antiderivatives and integrals, is that we need to include a plus c where c is any constant, because we know when we take a derivative with a constant that the constant drops off and becomes 0. So your example is if f of x equals 2x, then the antiderivative capital F of x is equal to x squared. But it could also be x squared plus 5, or x squared minus rad 2, or any infinite combinations where c is a constant value. So we're going to work together. Well, I'm going to work. You're going to watch me work through 4 antiderivative examples using some basic derivatives that we're familiar with. So from here, I've got f of x equals 3x squared, and I know that I must have taken the derivative of a cubic function to achieve an x squared. And then if I think about taking the derivative of x cubed, I know I'm going to bring a 3 out front, which is where this 3 comes from, so I don't need any coefficient on my antiderivative. And then I just need to make sure that I put a plus c for the constant. On the next one, we have 1 over x as the derivative, so we have to ask ourselves, what function does this come from? And this is really, it's very important that you have your basic derivative rules memorized, because if you do, then you know off the top of your head that the derivative of ln x is 1 over x. So the antiderivative of 1 over x is ln x. For the next one, we have cosine x. And again, knowing your derivatives like the back of your hand are really useful, because then you would know that the derivative of sine x is equal to cosine x. So the antiderivative of cosine x is sine x. Finally, e to the x is its own derivative, which means that e to the x is its own antiderivative. And so this is antiderivatives. We're basically taking derivatives in reverse. So an antiderivative is also referred to as, or can be referred to as, an indefinite integral. In formal notation, you have the integral symbol, which is this curly elongated s. And so the integral of f of x dx, remember dx is pronounced with respect to x, is equal to f of x plus c. So our example is the power rule for integrals. This is a rule for n not equal to -1. The integral of x to the n dx is equal to x to the power of n plus 1 over n plus 1 plus c. Now, why can't n be -1? Well, it's because if this is x to the -1, we know that the antiderivative is ln x. It's not another power function. So let's prove that this works. We're going to take dy dx of x to the n plus 1 over n plus 1 plus c. So with this, we'll apply the power rule, and we'll bring the n plus 1 forward. So we have n plus 1 times x to the n plus 1 minus 1 over n plus 1. And then the derivative of c is 0, so there's no extra here. The n plus 1s will cancel, and in our numerator, we have 1 minus 1 is x to the n. So this is how we show that the antiderivative rule for x of n is x to the n plus 1 over n plus 1 plus c. So on this next page, you just have a table of all your basic derivative rules and their indefinite integrals. So for example, the derivative of k, a constant, is equal to 0. So the integral of k is this. And it's just all the rules laid out, including the inverse functions over here. Inverse cosine isn't on this list. I'm not really sure, probably because it's so similar to inverse sine, but you got your basics. You have your reciprocal functions, you have your trig functions, your e, your l, and all that good stuff. So derivative rule on the left and integral rule on the right. Now, to verify an indefinite integral, you're basically just going to take a derivative and make sure it's true. So is x squared over 2 plus e to the x plus c the integral of x plus e to the x? Fastest way to check is to take d dx. So d dx of x squared over 2 plus e to the x plus c. Using our derivative rules, we can break this down into 3 separate terms. D dx c, and we're going to bring down that 2. The 2's will cancel. We're left with x plus the derivative of e is e, and the derivative of c is 0. So it turns out that this one works. Let's verify the next one. We're going to take d dx of x e to the x, so we got some power rule happening, minus d dx of e to the x plus d dx c. So let's do our power rule here. If we take this derivative, we are going to take the derivative of x, which is 1, and then e to the x, plus x times the derivative of e to the x, which is e to the x, minus the derivative of e to the x, which is e to the x, plus 0, the derivative of c. Here, we've got e to the x minus e to the x, and it turns out that this derivative is actually x e to the x, which matches. So we've also verified this identity. Not this identity, this statement. So both of these verify. The properties of indefinite integrals, so sum and difference, you just have a sum and difference. You can split those up. Constant multiple, you can bring your constants out front and leave them as a constant multiple. So if we're looking at this next one, this integral can be broken down into sums. So we've got 5x cubed dx. Make sure you carry that dx with each term, okay? Minus the integral of 7x squared plus the integral of 3x. Oh, there's supposed to be a dx right there. 3x dx plus the integral of 4 dx. Then we can take out, using our constant multiple rule, each of those coefficients. So this is 5 integral x cubed dx minus 7 integral x squared dx plus 3 integral x dx. And then this one, I guess it's plus 4 integral dx. So using our power rule that we defined up in the rules, we have 5, and then this one we bring it up 1, x to the 4th, and then divide it by that power, minus 7x cubed over 3, plus 3x squared over 2, and then over here we've got plus 4x. So if we simplify this fully, we've got our final solution that the integral of that polynomial is equal to 5/4 x to the 4th minus 7/3 x to the 5th, nope, that's a third, x to the 3rd, plus 3/2 x squared plus 4x. That doesn't look like an x squared. Over here, we're going to do a little algebra first. So I'm going to split that into 2 separate terms. This is x squared over x plus 4 cube root of x over x. And now I need it in parentheses because it's 2 separate terms, dx. And so that's going to give me the integral of x, if you simplify the first term, plus dx, plus the integral. Now over here, I'm going to bring that 4 out in front. I'm actually just going to clean this whole thing up. So x dx, bring out the coefficient of 4. And then I know x, cube root of x, it can also be written as x to the 1/3. So I'm going to go ahead and subtract those two. And I'm going to get x to the negative 2/3 dx. Then using my power rule, that's going to give me x squared over 2 plus 4 times, now raise that up and you're going to get x to the 1/3, but then you also have to put it over 1/3. So make sure you reciprocate that, because your final answer is x squared over 2 plus 12 cube root of x. Okay. Oh, plus c. Ooh, bad notation. Make sure you do not, under any circumstances, forget your plus c's. Keep going. So this one's a little more complicated than the last examples, but it's not really if you know your rules. So the first thing I'm going to do is take out the 4, and then if you think about that table again, this fraction is actually meant to look familiar. So I'm going to scroll all the way up back to our list of integral rules. So over here, we actually know that the derivative of inverse tangent is 1 over 1 plus x squared. So when I take the integral of 1 over 1 plus x squared, I should get inverse tangent of x plus c. And that's actually exactly what I have right here. So this just becomes 4 times the inverse tangent of x plus c. Now this one, you might be thinking, how do I integrate the product rule? And really the short answer is right now, we don't. This can be trigged just a little bit, where we know that tangent is the same as sine over cosine. So we have sine x over cosine x times cosine x dx. And those cosines cross out. So really this is just the integral of sine. And the integral of sine is negative cosine plus c. And that's just because the derivative of cosine is negative sine, but we're looking for a positive sign. So that introduces that extra negative. All right, we're going to finish up these notes with differential equations. A differential equation is an equation that relates an unknown function and one or more of its derivatives. A simple example is dy dx equals f of x. To solve this equation, you basically find your function y whose derivative is f, which is what we're doing when we're doing antiderivatives. So if we're looking for dy dx is equal to sine x, then we can take our integral and write y is equal to, because we're undoing, right? So dy dx turns into y, the integral of sine x, which is equal to negative, nope, not negative, is equal to cosine, yeah, negative cosine x. Didn't we just do this example? Plus some unknown constant c. Well, this problem goes a little bit farther and shows that when the input is 0, the output is 5. So we are going to say that 5 is equal to negative cosine of 0 plus c, and we're actually going to be able to find the value of c that makes this specific function work. So cosine 0 is 1, which makes this negative 1, and actually tells us that c is equal to 6. So my final answer for this differential equation is y equals negative cosine x plus 6. So this is the very specific antiderivative who satisfies the equation y0 equals 5. All right, last example is our applied example. If a car is traveling at a rate of 88 feet per second, or 60 miles per hour, when the brakes are applied, then the car begins decelerating at a constant rate of 15 feet per second. How many seconds elapse before the car reaches a complete stop? And so this is one of the most common applications of derivatives and integrals. And so this is your position, velocity, acceleration. So let's define a few things. We're going to let a of t be the acceleration at a specific time t. We're going to let v of t be the velocity at a specific time t. And we're going to let s of t be the position at a specific time t. And we just want to remind ourselves that velocity is the derivative of position and acceleration is the derivative of velocity. So first we see that the initial velocity is 88 feet per second. So we can say v0 is equal to 88 feet per second. And that's the exact moment that the brakes are applied. So we're going to let brakes are applied be t equals 0. Then the car begins decelerating at a constant rate of 15 feet per second squared. So this is our a naught. So this is our deceleration or our acceleration at 0, but because it's a constant rate, it's actually our acceleration at all moments. Because it's losing velocity, it's decelerating, we want to make sure that that's negative 15 feet per second squared. And so what we've basically set up is an initial value problem like the one above, because v prime of t is equal to at, which means the integral of at is equal to vt. So we're going to take this integral. Yep. So the integral of negative 15 feet per second is negative 15 t plus c. And we set that equal to vt. Well, we have a specific point. We know that v0 is 88. So we can set this equal to 88. And that's at time 0. And so that's going to cancel out. And so we get that the constant is equal to 88. So our full equation is now, I'm kind of running out of room here, vt equals negative 15 t plus 88. So this first question says, how many seconds before the car stops? Well, the car stops when its velocity is 0, and that implies it's no longer moving. Oops, I think I wrote 0, even though I said 88. So we're going to take this velocity equation, and we're going to set it equal to 0 to find the moment that the car stops. Plus 88, 15t equals 88, and then whatever 88 divided by 15 is, so we got about 5.87 seconds before the car stops. How far does the car travel during that time? So again, we've got another antiderivative to get to our distance equation. Since we're trying to find the distance traveled from the minute the brakes are applied, we're going to let the distance at t equals 0, so s0 equals 0, because then whatever distance we travel is just added on to 0. So defining s0 equals 0, we've basically got another initial value problem, because we have vt equals negative 15t plus 88 from our part A answer, and we're going to integrate that. And that's going to give us our st. So starting here, imagine that negative 15 is a constant multiple. So we've got t squared over t as the integral of t with a negative 15 coefficient. And then 88 is going to become plus 88t, and then plus some constant, which in this case, since we're defining 0, 0, when we plug in 0, we're going to get that c equals 0. And so I'm just going to be clever here, turn that into 0. So this is our st, and we know that it takes the car about 5.8 seconds to stop, 5.87 seconds to stop. So we just plug that 5.87 seconds in for our equation. It might even be better if we use the answer function of our calculator or leave our answer exact as the 88 over 15. So we're going to do 88 over 15, quantity squared, divided by 2, times negative 15, plus 88 over 15 times 88. And so we get the result of about 258.1-ish feet. So that concludes the video notes for antiderivatives. Thank you for watching.